Today we're diving into the fascinating world of deep learning. As powerful as deep learning is, it comes with its own set of challenges that can stump even experienced practitioners. In this video, we'll explore the most common obstacles faced in deep learning projects and, more importantly, how you can overcome them. Whether you're a beginner or a seasoned developer, understanding these hurdles and their solutions will help you build better, more reliable models. Let's start by setting the stage and looking at why deep learning is both exciting and demanding. One of the first and most significant challenges in deep learning is dealing with data quality. Deep learning models thrive on large, clean, and well-labeled datasets. However, in reality, data can be messy, incomplete, or inconsistent. Poor data quality can lead to inaccurate models and unreliable predictions. To address this, it's crucial to invest time in data cleaning, preprocessing, and augmentation. Techniques like handling missing values, removing duplicates, and normalizing data can dramatically improve your model's performance. Another common hurdle is having too little data. Deep learning models typically require vast amounts of labeled data to perform well. When data is scarce, models may overfit or fail to generalize. To overcome this, you can use data augmentation techniques such as rotating or flipping images or generating synthetic data. Transfer learning is also a powerful approach, where you leverage pre-trained models and fine-tune them on your smaller dataset. These strategies help you make the most of limited data. Overfitting is a classic problem in deep learning. It happens when your model learns the trained data too well, including its noise and outliers, but fails to perform on new unseen data. This leads to poor generalization. To combat overfitting, you can use techniques like dropout regularization and early stopping. Additionally, ensuring you have enough diverse data and using simpler models can help. The key is to strike a balance between model complexity and the amount of data you have. The flip side, underfitting occurs when your model is too simple to capture the underlying patterns in the data. This results in poor performance on both training and test sets. To address underfitting, you can increase model complexity by adding more layers or neurons, or by choosing a more sophisticated architecture. Also, make sure your data is well prepared and that you're not oversimplifying the problem. Sometimes more training time or better features can make a big difference. Deep learning models, especially large ones, require significant computational resources. Training can be slow and expensive without the right hardware. GPUs and TPUs are commonly used to speed up training, but not everyone has access to these. Cloud computing platforms offer scalable solutions, allowing you to rent powerful machines as needed. Efficient coding practices such as optimizing batch sizes and using mixed precision training can also help make the most of available resources. Training deep learning models can take hours, days, or even weeks, depending on the size of your data and model. Long training times can slow down experimentation and progress. To speed things up, consider using smaller models for prototyping, distributed training across multiple machines, or techniques like early stopping to halt training when improvements plateau. Regularly monitoring your training process helps you identify bottlenecks and optimize your workflow. Using the right hyperparameters, such as learning rate, batch size, and number of layers, is critical for deep learning success. However, tuning these parameters can be time-consuming and complex. Automated tools like grid search, random search, and Bayesian optimization can help streamline this process. It's also helpful to start with recommended defaults and adjust based on validation performance. Remember, systematic experimentation is key to finding the optimal settings for your model. Deep learning models are often criticized for being black boxes. It's hard to understand how they make decisions. This lack of interpretability can be a challenge, especially in sensitive applications like healthcare or finance. To improve transparency, you can use techniques such as feature importance analysis, visualization of activations, or model-agnostic tools like LIME and SHAP. These methods help you gain insights into your model's behavior and build trust with stakeholders. Labeling data for supervised learning can be a daunting and expensive task, especially for large datasets. High-quality labels are essential for training accurate models, but manual labeling is time-consuming and prone to errors. To address this, consider using semi-supervised learning, crowdsourcing, or active learning techniques. These approaches can help reduce the labeling burden while maintaining data quality, making your deep learning projects more efficient. Class imbalance occurs when some classes in your dataset are underrepresented compared to others. This can lead to biased models that perform poorly on minority classes. To tackle class imbalance, you can use techniques like oversampling the minority class, undersampling the majority class, or applying class weights during training. Synthetic data generation such as SMOTE is another effective strategy. Addressing class imbalance ensures your model treats all classes fairly. Data leakage happens when information from outside the training dataset is used to create the model, leading to overly optimistic performance estimates. This can occur through improper data splitting or feature selection. To prevent leakage, always separate your training, validation, and test sets, and ensure that no information from the test set leaks into the training process. Careful data handling is crucial for building trustworthy models. While deep learning models can automatically learn features from raw data, thoughtful feature engineering can still make a big difference. Selecting relevant features, creating new ones, or transforming existing ones can improve model performance and training speed. Automated feature engineering tools can help, but domain knowledge remains invaluable. Experiment with different feature sets and transformations to see what works best for your problem. Using the right model architecture is a critical decision in any deep learning project. With so many options available, from simple feed-forward networks to complex transformers, it can be overwhelming. Start by understanding the strengths and weaknesses of different architectures for your specific task. Experiment with a few models and compare their performance using validation data. Remember, the best model is not always the most complex one. Deploying deep learning models into production environments can be challenging. Issues like model size, inference speed, and compatibility with existing systems often arise. To ease deployment, consider model compression techniques such as quantization or pruning and use frameworks that support efficient inference. Testing your model in a staging environment before full deployment helps catch potential issues early. Once your model is live, monitoring its performance is essential. Data drift, unexpected inputs, or changes in user behavior can degrade model accuracy over time. Set up monitoring tools to track key metrics and detect anomalies. Regularly retrain your model with fresh data to maintain performance. Proactive monitoring ensures your model continues to deliver value in real-world settings. As your application grows, your deep learning model must scale to handle increased demand. Scalability challenges include managing larger datasets, serving more users, and maintaining low latency. Solutions include distributed training, model parallelism, and using scalable cloud infrastructure. Planning for scalability from the start helps you avoid bottlenecks as your project expands. Deep learning models can be vulnerable to security threats, such as adversarial attacks or data poisoning. Protecting your models and data is crucial, especially in sensitive applications. Implement security best practices such as input validation, monitoring for unusual activity, and keeping your software up to date. Regular security audits help identify and address potential vulnerabilities. Ethics play a vital role in deep learning. Issues like bias, fairness, and transparency must be addressed to ensure responsible AI development. Regularly audit your models for bias, involve diverse stakeholders in the development process, and be transparent about how your models make decisions. Ethical AI benefits everyone and builds trust in your solutions. The field of deep learning evolves rapidly with new techniques and breakthroughs emerging all the time. Staying up to date can be overwhelming. To keep pace, follow reputable journals, attend conferences, and participate in online communities. Continuous learning and experimentation are key to staying ahead in this dynamic field. Managing different versions of your deep learning models is essential for reproducibility and collaboration. Version control tools, such as Git for code and specialized platforms for models, help you track changes and roll back if needed. Documenting your experiments and configurations ensures you can reproduce results and share your work with others effectively. Reproducibility is a cornerstone of scientific research, but achieving it in deep learning can be tricky. Differences in hardware, software, or random seeds can lead to inconsistent results. To improve reproducibility, fix random seeds, document your environment, and use containerization tools like Docker. Sharing code and data openly also helps others replicate your work. Handling large datasets is a common challenge in deep learning. Storing, processing, and loading massive amounts of data efficiently requires careful planning. Use data pipelines, batch processing, and efficient storage formats to streamline your workflow. Cloud storage solutions can help manage scale, while data generators allow you to load data on the fly during training. Noisy data, or data with errors and inconsistencies, can negatively impact model performance. To handle noise, apply data cleaning techniques, use robust loss functions, and consider outlier detection methods. Sometimes collecting more data or using ensemble models can help mitigate the effects of noise. The goal is to ensure your model learns meaningful patterns, not just noise. Transfer learning allows you to leverage pre-trained models on large datasets and adapt them to your specific task. This approach is especially useful when you have limited data or computational resources. By fine-tuning existing models, you can achieve high performance with less effort. Transfer learning has become a standard practice in many deep learning applications, from image recognition to natural language processing. Regularization helps prevent overfitting by adding constraints to your model. Common techniques include L1 and L2 regularization, dropout, and data augmentation. These methods encourage your model to learn general patterns rather than memorizing the training data. Experiment with different regularization strategies to find what works best for your problem. Early stopping is a simple yet effective technique to prevent overfitting. By monitoring your model's performance on a validation set, you can halt training when improvements plateau. This not only saves time and resources but also helps your model generalize better to new data. Implementing early stopping is straightforward and can be a valuable addition to your training process. Batch normalization is a technique that normalizes the inputs of each layer in your neural network. This helps stabilize and accelerate training, making it easier to use higher learning rates in deeper models. Batch normalization can also act as a form of regularization, reducing the need for other techniques. Incorporate batch normalization layers to improve your model's training dynamics. Choosing the right learning rate is crucial for effective training. Learning rate scheduling involves adjusting the learning rate during training, often reducing it as the model converges. Popular schedules include step decay, exponential decay, and cyclical learning rates. Proper scheduling can lead to faster convergence and better final performance. Deep networks can suffer from vanishing or exploding gradients, making training unstable or slow. This issue is especially common in very deep or recurrent networks. Solutions include using proper weight initialization, batch normalization, and gradient clipping. Choosing appropriate activation functions like RayLU can also help mitigate these problems. The optimizer you choose can significantly impact your model's training speed and final accuracy. Popular options include SGD, ATOM, and RMSprop, each with its own strengths. Experiment with different optimizers and tune their parameters to find the best fit for your problem. Sometimes, switching optimizers during training can yield better results. Any real-world datasets contain categorical features which must be properly encoded for deep learning models. Common encoding methods include one-hot encoding, label encoding, and embedding layers. The choice depends on the number of categories and the nature of your data. Proper encoding ensures your model can effectively learn from all available information. Data augmentation is a powerful technique to increase the diversity of your training data without collecting more samples. Common methods include rotating, flipping, cropping, or adding noise to images. For text or audio, you can use techniques like synonym replacement or time stretching. Augmentation helps your model generalize better and reduces overfitting. Deploying large deep learning models can be challenging due to size and speed constraints. Model compression techniques such as pruning, quantization, and knowledge distillation help reduce model size and improve inference speed. These methods make it feasible to deploy models on edge devices or in resource-constrained environments. Deploying deep learning models on edge devices like smartphones or IoT sensors introduces unique challenges. Models must be lightweight and efficient to run on limited hardware. Techniques like quantization, pruning, and using specialized frameworks can help. Edge deployment enables real-time inference and reduces reliance on cloud connectivity. Explainable AI, XAI, focuses on making deep learning models more transparent and understandable. Techniques like attention mechanisms, saliency maps, and model-agnostic explanations help users and stakeholders grasp how decisions are made. XAI is especially important in regulated industries where accountability and trust are paramount. In dynamic environments, models must adapt to new data and changing conditions. Continuous learning, or online learning, allows models to update incrementally as new data arrives. This approach helps maintain accuracy and relevance over time, especially in applications like recommendation systems or fraud detection. Deep learning projects often involve collaboration among data scientists, engineers, and domain experts. Effective communication and clear documentation are key to successful teamwork. Use collaborative tools, version control, and regular meetings to keep everyone aligned. Diverse perspectives lead to better solutions and more robust models. Managing computational and human resources efficiently is crucial in deep learning projects. Prioritize tasks, allocate resources wisely, and automate repetitive processes where possible. Cloud platforms and workflow management tools can help streamline operations and reduce costs, allowing your team to focus on innovation. Good documentation is essential for reproducibility, collaboration, and maintenance. Document your data sources, preprocessing steps, model architectures, and training procedures. Clear documentation helps others understand your work and makes it easier to revisit projects in the future. Invest time in writing thorough and organized documentation. Maintaining deep learning models after deployment is an ongoing process. Monitor performance, retrain with new data, and update models as needed to address changing requirements. Regular maintenance ensures your models remain accurate and relevant, providing lasting value to your organization. Deep learning applications must comply with legal and regulatory requirements, especially in sectors like healthcare, finance, and privacy-sensitive domains. Stay informed about relevant laws such as GDPR and ensure your data handling and model usage align with regulations. Legal compliance protects your organization and builds user trust. Incorporating user feedback into your deep learning models can drive continuous improvement. Collect feedback through surveys, usage data, or direct communication. Use this information to identify areas for enhancement, retrain models, and refine features. Engaging users in the development process leads to better products and higher satisfaction. Applying deep learning to new domains or industries presents unique challenges. Domain adaptation techniques, transfer learning, and collaboration with subject matter experts can help bridge the gap. Be prepared to experiment and iterate as you tailor your models to new applications and data types. Wrap up: deep learning is a powerful tool with immense potential, but it comes with its own set of challenges. By understanding and proactively addressing issues like data quality, overfitting, resource constraints, and ethical concerns, you can build robust and effective models. Remember, continuous learning, collaboration, and adaptability are essential for success in this ever-evolving field. Thanks for joining us on this journey through the common challenges in deep learning and how to overcome them.